4.5, applications of congruences. So in the first section in this chapter, 4.1, we looked at the basics, these kind of basic number theory ideas. So here, if we have two integers a and b, what does it mean for a to divide b? It means a divides evenly into b with no remainder. In other words, a is a factor of b. Or you could also say b is a multiple of a. And a divides b has this notation, just a vertical line. It's, don't get confused. So a over b, this is the fraction. This is not a fraction. It's really a proposition. It's true or false. So it's true when a divides b. We have this notation, a mod m. That means the remainder when you divide a by m. M is called the modulus here. Alright, so if you divide a by m, well, if m divides a, then there's no remainder. But in general, there'll be a remainder, and the remainder has to be between 0 and m minus 1. Okay, so when you see this notation, it means a remainder. And lastly, this notation, so you read this a congruent to b mod m, or modulo m. So this means that the difference, a minus b, well, m divides that difference. That's the same as saying m divides b minus a. And we saw another way to think about this is that if you divide a by m, and if you divide b by m, you'll get the same remainder. So this key idea in number theory is this idea of dividing evenly with no remainder, or maybe there is a remainder. So this section we look at applications of these ideas. So some simple applications, but useful. The first topic is hashing functions, and these have applications in cryptography, data storage, and error checking. You will see an example of that later as well, with check digits. But the basic idea is to reduce bigger numbers to smaller numbers of a fixed size. Alright, so these are also called one-way functions. We're losing information, but this is a useful thing to do sometimes. And a simple way to go from a bigger number to a smaller one is using remainders. Example 1, let the hashing function h of k, so h is the name of the function, k is the input, be defined by h of k is equal to k mod 100. find h of this number and h of this number. Alright, so we're hashing here is just taking the number and looking at the remainder when you divide by 100. Okay, well, what happens if you divide this first number by 100? Well, on your calculator, yeah, you'll get this, or just remember dividing by 100 moves the decimal point 2 places to the left. So we can see the quotient. So 100 divides into this number 1,234 times, but there's a decimal, so it doesn't divide in evenly. What's the remainder? Well, if you multiply the quotient by the number you're dividing by, the 100, you'll see that there's a 56 left over. Alright, so the value of the hashing function for this number is 56. That's also called the hashing value. Alright, so we've certainly reduced a bigger number to a smaller number. If you remember in our discussions of functions, so what's the range of this hashing function? Well, you can see it's a remainder when you're dividing by 100, so we know the remainders have to be numbers between 0 and 99. So that's the range. And this one's kind of in the middle. And the other example, so what's the hashing value for 9172? Well, if you divide this by 100, the remainder is 72. And you probably see a pattern. If you divide a number by 100, the remainder is just those last two digits. So that's easy to see. Also, this function h, it's not one-to-one. So there are lots of numbers that have the hashing value 72. So any number whose last two digits are 72 is going to have hashing value 72. So this is not a one-to-one function. When this happens, it's called a collision of the hashing function. So good hashing functions try to avoid collisions as much as possible. So you want to have the numbers kind of evenly, the hashing values evenly distributed. Alright, so this h, it's an example of a function that's onto but not, it's onto if the codomain is 0 to 99, but it's not one-to-one. Okay, in the book, there's some similar examples. So using hashing functions to send social security numbers to memory locations. That could be an application. Here the modulus is 111. Okay, so this hashing function takes a social security number and looks at the remainder when you divide by 111, and it'll use that as a memory location to store information about this customer. So find the memory locations assigned to these two social security numbers. Okay, so we've changed the modulus from 100 to 111 here. Okay, so how do you work this out? So this, we have a bigger number. It's the same idea though. You want to divide it by 111 and see what the remainder is. So yeah, just to clarify that, so on your calculator, you can again do the division. You'll get a decimal, so there is some remainder. This first piece, this is the quotient, so that's the number of times 111 fits into this number. Okay, so then if you multiply this by the divisor and subtract that from the original number, then that gives you the remainder. Alright, so yeah, so usually A is equal to dq plus r, so we're just subtracting the dq from both sides to find the r. Alright, so that's how you can work out remainders for these bigger numbers. Okay, so check that you get 14. So in this example, yeah, this customer is going to have their information stored in location 14, and this other customer gets their information stored in location 65. So yeah, so there's only 111 different storage locations, so limited storage. If you have two customers with getting the same hashing value, even though they have different social security numbers, so this other number also gives 14. So then, yeah, when there's a collision like that, you have to have some extra programming to figure out where to store this so yeah, you can't store them in the same place, or maybe you can, so that's a whole other question. But just the basics of this hashing function is just a simple way to get from big numbers to smaller numbers. Okay, next application, pseudo-random numbers. Can you read that? Yes, so random, pseudo means kind of fake. Yeah, so these are fake random number sequences. Yeah, there's nothing random about a computer. following a program, but we can kind of simulate randomness, and that's what's happening here. So we use this linear congruential method to make sequences of random looking numbers. So fix 3 positive integers. So we have these parameters. So m is the modulus, a is called the multiplier, and c is the increment. Okay, so we're multiplying by the multiplier, we're adding c. Okay, and we use these numbers to construct a sequence, an integer sequence. X sub 0, that's going to be the first integer. Yeah, we can pick this separately. That's called the seed. So the first integer. Okay, and then this method produces the next number, x sub 1, and then produces the next one, x sub 2, based on x sub 1. So it just steps along making new numbers. How does it work? Well, okay, so we picked some x sub 0, so then we calculate a times x sub 0 plus c. Okay, so the seed gets multiplied by a, the multiplier, and increased by c, the increment. And then we work that out mod m, so just divide this by m, find the remainder. Okay, and that remainder, that's the next number in the sequence. Okay, so it's a remainder mod m, so it has to be between 0 and m minus 1. Okay, so all of these numbers are between 0 and less than the modulus. The next number, x sub 2, is found the same way, but now it uses the last number. So it's a times x sub 1 plus c mod m. Then x sub 3, so you keep using this method. In general, x sub n plus 1 is a times x sub n plus c mod m. So each number in the sequence depends on the one before, and a sequence like this is called recursive. This is an example of recursion. Let's see an example. So compute the first 3 numbers after the seed 11 using modulus 15, multiplier 13, and increment 5. So the seed is 11, so the first number, x sub 0, is 11. And then the next number, x sub 1, is the multiplier is 13, increment 5, so it's 13 times the first number plus 5. 13 times 11 plus 5, that's 148. And then work that out, mod 15, you get 13. So the remainder, when you divide 148 by 15, is 13. So that's x sub 1. Okay, now this number goes into the formula. So multiply it by 13, add 5 to get 174. and that mod 15 is 9. You can check. So x sub 2 is 9, and then one more x sub 3. Just repeat. We'll get 122 mod 15, which is 2. Alright, so the sequence starts like this. You could keep going. The point is these are kind of random looking numbers, at least. But if your modulus is 15, then this is soon going to start to repeat. So in practical applications, you'd have a much bigger modulus. One in the book. Example 3 here. Find the sequence generated with modulus 9, multiplier 7, increment 4, and seed 3. Alright, so the same deal, just different numbers. So starting with 3, so x sub 0 is 3, x sub 1 is 7 times 3 plus 4. That's that 25, and then 25 mod 9. So 9 goes into 25 2 times, that's 18, remainder 7. Alright, so with these numbers, we get this sequence 3, 7, 8, 6, 1, 2, 0, 4, 5, 3. Okay, now we've got back to the beginning, so then it'll just repeat after that. So it's a repeating sequence, so not really random. But it looks random at the start, at least. Alright, and the last application of these congruences or remainders, that's check digits. So many identifying numbers, like bank account numbers, credit card numbers, ISBN numbers. If you look in the beginning of a book, you'll see it. Every book has a number. UPC numbers for retail products. All of these identifying numbers usually, these ones do contain check digits. And these check digits can usually detect if a number is not correct. For example, if you make a mistake typing in your credit card number when you're buying something online. So if you've ever noticed, I think I've certainly noticed, if you make a mistake, then the system tells you right away, that's not correct. So how does the system know that you've made a mistake? Does it have a list of every credit card number? No, it's a simpler system. It just, every credit card has a check digit built in. So we can look at the actual system credit card numbers use. It's pretty simple, and it's a nice application of remainders. All right, so credit card number. Again, I'm not using any real credit card numbers, but credit card number, it's 16 digits. Yeah, so each digit is 0 through 9. And the digit on the right, that's the check digit. So in this example, the check digit is 8. So how does it work? So so the first 50 numbers, that's the real identifying information. And then you can calculate the check digit using the Lun algorithm. Okay, so let's just look at the first 15 digits. Just ignore that 8. So we're going to calculate that 8. Let's underline every other digit. Okay, and these digits get doubled. Okay, so multiply these underlined digits by 2. So this 4 turns into an 8. The 2 stays the same. We multiply the 9 by 2 and get 18, but any numbers that are bigger than 9, we're going to add their digits. Okay, so 2 times 9 is 18, but that's too big, so add the digits. 1 plus 8 is 9. Bring down the 8. 1 times 2 is 2. Bring down the 3. 6 times 2 is 12. That's too big. But we can make it smaller by adding the digits. So 1 plus 2 is 3. All right, does that make sense? So just every other digit gets doubled. But for a number like 8, if when you do the doubling you get something bigger than 9, then just look at its 2 digits, add those together to get a number less than or equal to 9. Okay, so this 8 turns into a 7. All right, so that's the first part. Okay, so we get a new 15-digit number, and then we add up all those digits. Okay, so 8 plus 2 plus 9 plus 8. So add those all together. In this case, you get 72. And so what is the check digit? Well, the idea is you want to add a number here, add something to the 72 so that you get something with the remainder 0 when you divide by 10. All right, so adding 8 to 72, we get to 80, and 80 mod 10 is 0. All right, so we want to add a number on the end here, a digit, so that when you add up all these guys, you get something that has remainder 0 when you divide by 10. So that's why the check digit is 8 here. All right, so this 8, it's So if you make a mistake typing in one of these numbers, then when you go through this procedure, you're no longer going to get 0 when you work out this sum mod 10. You'll get some other number, 1 to 9. Alright, so that's how it works. Any mistakes are going to change that remainder from 0 to something else. Alright, but if you make more than one mistake, it is possible that 2 mistakes can kind of cancel out and you get back to 0. But that's kind of unlikely. If you make a bunch of mistakes, then there's only a 10% chance that the remainder will be 0. It's more likely to be 1 through 9. Okay, so this is, it's a whole field of error detection. So this is a simple way to check for errors in identifying numbers, like credit card numbers. Okay, so example 3. Suppose you type this number in when you're doing your online purchase. Is the computer going to object? So is this a valid credit card number? Alright, so we'll use the Lund algorithm again. Alright, so this time the check digit is included, that's the 1. So starting with the first number, we double every other digit. So here we got 12, and that's too big, so we add the digits. We get 3, 7, 8 times 2 is 16, add the digits. Okay, also this, for the 6, we have to add the digits. Alright, so we get this new 16-digit number. And so add its digits. So 3 plus 7 is 10, 17, 26. So add them all up, and this time we get 73. And 73 mod 10 is 3. So that's not equal to 0. So that means this is not a valid credit card number. So if I type this in, then I definitely made a mistake. Okay, so it's only valid if we get a sum, so that sum mod 10 is equal to 0. Alright, so that's how check digits work. There's other examples here. So these numbers at the start of books, those have a slightly different check digit procedure. Alright, so that's some simple applications of this modular arithmetic, looking at remainders.